Welcome back. In today's lecture, I am going to talk about the linearization about the origin. Okay, and I hope that you have already learned this kind of technique in the linear control course or modern control course, as well as nonlinear control course also I have taught this. Okay, but here we are going to see that why linearization works in the neighborhood of equilibrium point only, and at how much extent I can talk about the stability of the original nonlinear system by looking towards the linearized system. Means linearized system means that is either linear time invariant or time varying. Okay, so I will check the stability of linear time varying system or linear time invariant system, and after that I am going to talk about the stability of the original system. Okay, and due to that reason this method is also called Lyapunov indirect method. Okay, so first I am going to start with the autonomous system x dot equal to fx, and after that what I am telling that suppose this system, this x dot equal to fx, their mathematical model is valid in this particular domain. This kind of assumption I am using almost everywhere. I am also assuming that f is locally Lipschitz, and d, you can, if you assume that whatever set d that is compact set, then I can tell that there exists a unique solution. Okay, so that kind of things I have already assumed, and 0 is the my equilibrium point without loss of generality. Okay, so when I have discussed about the linearization, at that time I was talk about the mean value theorem. Okay, so my mathematical model is basically valid in this region D. After that what I am going to do, suppose I have selected this ball where my future trajectory is going to lie. So, and this is my origin. So how to apply mean value theorem? Suppose this is x, so I will select some point z high or z in between these 2 points. Suppose this is z high point, then I can write f high x, means since f has n number of component, because x belongs x is subset of d and d belongs to Rn. So I have n number of component like this. So I am going to check each and every component, and across each and every component I am going to apply the mean value theorem. Okay, please check. I have already derived this kind of condition in previous class. I think that it might possibly in 10th class or 9th class. I don't remember exactly. Okay, so now what we found that since 0 is my equilibrium point, so without loss of generality, this term, because some f0 is some kind of column vector, so this kind of column vector is 0, it means that each and every entry equal to 0, so this equal to 0. So finally I have this kind of things, whatever written I have here, same kind of things I have copied here. After that, now what I am going to do, I am going to add some kind of partial derivative of fi with respect to x in the neighborhood of equilibrium point, and same point I am going to subtract. Okay, after that we will see that how much extent, why basically we have done, because I want to check that at how much extent I can talk about the stability of nonlinear system after the linearization. Okay, so what I am telling that I have extracted the linear part, and after that I have certain kind of nonlinear part, and based on some kind of condition on nonlinear part I can talk about the stability of the equilibrium point x equal to 0. Okay, so gx, you can see here that dou fi by dou x zi minus dou fi by dou x into 0, so that kind of relation, and x is here. Okay, so I have actually added, I have subtracted, same kind of things, and this part is dou f by dou x about x equal to 0, that is nothing but if you substitute x equal to 0, then same kind of terminology comes into picture, that is linear part. Okay, and after that what I am assuming, I am going to check each and every component of this nonlinear part, and it is possible to show that this is actually, since I have gi equal to this, so if I will take the norm here, gi is, since fi has n number of n number of entry, and after that I am going to calculate partial derivative with respect to each one, x, x1, x2, x3. Okay, so somehow this we will end up with some kind of Jacobian matrix. Okay, and if you check just first entry of Jacobian matrix, similarly I have n number of entry, so first entry I have defined as a gix, and it is possible to show that if I will take norm, then norm will spread on both sides, and after that, now by the continuity of this gix, it is possible to show that as x tending towards 0, then gi by x, that is also tending towards 0. Okay, because I am assuming that whatever vector field, that is continuous. Okay, so if vector field is continuous, then by the result of continuity I can tell that if something is continuous and 0 at the 0, then what we have to do, I can create two balls. We have already seen the definition of continuity. So for every or any, you can tell, gamma greater than 0, there exists a r such that I can give guarantee that if x that is less than r, they are mapping, continuous mapping, that is gx, that is going to live inside this kind of region. Okay, so this kind of things basically comes from the continuity principle. Anyone has confusion on this, then please let me know. Anyone?
So please explain the above relation again. Gx, so norm by x norm.
Okay, here, up to here, any confusion? This?
No, sir.
Okay, after that, what I have done, I have taken the norm on both side. Okay, so here you can see that what happens, that I have g1 g11 g12 up to gnn, some kind of things come into picture 1n, and similarly I have gn1 up to gnn, this kind of things comes into picture. Are you able to follow this, why I have written like this? Because
Yes,
here
sir. Jacobian type of things.
Jacobian kind of things is there. So actually I have taken Jacobian with respect to x and zi, Jacobian fi with respect to x and 0, and x is here. Due to that reason, this is r n cross n matrix, and I have x is already n cross 1 matrix, so that will remains consistent. Here I have x dot, in this side I have x dot, so that remains consistent with that. After that, now you can see that if I will pick this particular row, then what happens, gi represent this whole row. So, and if so, I have some kind of vector or some kind of transpose of column vector. So how to calculate the norm of that vector? I can check each entry, and after that I will calculate the norm. So I am telling, okay, I know that some way to calculate norm, and right hand side I also know. So right hand side I have multiplication of two quantity, one is matrix and another is x. So I have something equation like this, x equal to mx my. Now what I am going to do, I am going to take the norm, either you can take the absolute value or norm, that doesn't matter. So, and after that what happens, that I have m into y, norm of this, so I can write norm of m and norm of y like this. Okay, so due to that reason, this term comes into picture. So either you can take here absolute value or norm, both are the same. Okay, because if you are just assuming that this is a column vector, then I am telling, okay, that this symbol represent the absolute value, but that is not a norm you can write, then things become more transparent. Now what I am going to do, here, that I can interpret this thing gi, if gi is less than, retain like some quantity like this and mod x. Okay, so now you can see here that what I can write here, that I can, here everything is one dimensional gi after taking the absolute value. So I have divided both sides by absolute value of x, and I am assuming that I am going to exclude some point where x equal to 0. So I am just worrying the neighborhood of that. So at their neighborhood, that x that is tending towards 0. Now you can see that here, since x tending towards 0, so obviously by continuity, since x tending towards 0, so fi x is the equilibrium point, so that is also tending towards the 0. So basically, and what is z? Z is the distance from equilibrium point, and here x is there, x is here, and z is lying here. So you are decreasing the x. So basically we are tending towards this. So this quantity is also tending towards 0, and this quantity is obviously tending towards 0, because I am calculating dou f by dou x about the about the 0. So basically, as z tending towards 0, so I can tell that okay, even if this is finite quantity, same quantity will appear here. Since z is tending towards 0, so this quantity and this quantity is exactly equal, and due to that reason this is tending towards 0. So I have this kind of relationship.
Okay, sir.
Okay, now let us try to understand that whenever I am writing this, then what does it mean? Okay, in another way, what basically we are telling, I have two domains where x is lying, and another domain gx is lying. G is function from this to this. Now how basically we are defining the continuity? In order to define the continuity, I have selected some ball here in this particular region, and corresponding to that I will see the ball. Okay, so what is ball here? Origin is here. Origin will make to 0, because 0 is the equilibrium point without loss of generality here. So gx, even if you will put z I equal to 0, because z I is the distance from here to here, so this is 0. So this and this is going to cancel out. So basically now you can see that g0 is also 0. So I have to create ball in this side. And what kind of ball I have basically created? I am created some kind of epsilon ball, you can take. So corresponding to epsilon ball, there exists a delta ball, such that I can tell that if I start on this ball, then I am going to remain inside this particular ball. Okay, so now what basically we are telling now, that I have some kind of relation. Now what I am going to do, by continuity I am going to check this particular quantity. So I have function now gx is the function. So I am telling that for every epsilon greater than 0, there exists a delta that is depending on epsilon greater than 0, such that I can able to write that if x minus 0, that is going to remain in the epsilon ball, then that implies gx and 0 will map to 0, that is going to lie inside the delta ball. So in this way I can able to write. Okay, so now what I am going to do here, so now I know that here x less than equal to epsilon, and delta here, delta ball I can select any kind of delta ball. Sorry, after selecting delta ball I can able to select the epsilon ball. Now what I am going to do, I am going to select delta ball, that is function of dx. Okay, so what happens, that the multiplication of this, as this tending towards 0, then automatically I want to see that what is effect of this. And due to that reason, what I am telling that okay, if this is very close to r, then this relation is always satisfied. Now is it become clear, or any confusion? Then please let me know. So this result is coming from the continuity. Okay, you can also interpret in some another way. What kind of way you can interpret? You can see here that if I am writing like this, then what kind of condition this is? Anyone? Is it possible to interpret this gx function? Okay, if gx by x, I can able to assume that that is something, that this is the Lipschitz constant or not. Anyone? Is it possible to interpret this as a Lipschitz constant or not? L. Anyone has confusion on this? Then please let me know. because as zi tending towards 0, so I can tell that okay, there exists some kind of matrix. I don't know matrix, so basically there exists, because I am in compact region, so this quantity is some kind of some kind of quantity comes into picture. And since fi is some kind of continuous function, so continuous function is always bounded, so I can tell that okay, with respect to x, that is uniformly continuous, so this remains the bounded, and that is L, and due to that reason I can able to write this kind of relation, okay. So I mean to say that as x is going to lie inside R, then gx, that is going to lie inside this, okay. And gx, as x tending towards 0, then I have to make sure that this quantity, this ratio gx by mod x, that is also tending towards the 0, okay. It means that if R is finite, then gamma is finite, okay. So this relation basically comes due to the continuity property, okay. Up to here anyone has confusion? Anyone? Okay. Now what I am going to do, just I am going to tell that whenever I have some kind of nonlinear system, and if gx will satisfy this kind of bond, bond is like this, gamma mod x2, and x2 is nothing but that is less than R, okay. This kind of condition, if that this kind of condition is satisfied, you can see here that this system remains the linear system. Why this system is linear system when x is very less than 0? Because if you see carefully, then that is gamma mod x, and if you take the norm of this, that is also a mod x, okay. So somehow if you see carefully, then that will satisfy the Lipschitz condition. A means a norm of a minus some quantity a and mod x, okay. So slope of this system I am telling that again less than the L, that kind of things is there, okay. So this is the interpretation of the condition. Now let us come to the Lyapunov indirect method. So what basically Lyapunov indirect method is telling, suppose if I have some system, non-autonomous system like this, x dot equal to fx, and x equal to 0 is the equilibrium point, and you can see here one more important thing I am telling, that fx, whatever fx function, that should be continuously differentiable. If that is not continuously differentiable, then I cannot tell that whatever relation I have just written, that gx is bounded by gamma mod x, that is no longer true. So in order to make sure, because gx is depending on f, due to that reason I am assuming that that is continuously differentiable, okay. So if fx is not continuously differentiable, I cannot able to apply this kind of theorem, okay. So please be careful whenever you are linearizing, at that time I have to make sure that this is continuously differentiable. And in neighborhood of x equal to 0, if a is given like this, then what one can tell, that by checking this Jacobian matrix A, origin is asymptotically stable if real part of this Jacobian matrix A, that I have represented as a lambda I, that is strictly less than 0 for all eigenvalue. If this condition is satisfied, then I can talk about asymptotic stability of the origin of the original nonlinear system, okay. So I am telling that this nonlinear system x equal to 0 is asymptotically stable, obviously locally, because I have in the vicinity of x equal to 0, and you know that here I have two conditions, this kind of condition, and after that I know that x2 should be less than R, okay. So whatever result I am talking, that is only true in this particular region, okay. So in this particular region, origin is locally asymptotically stable, origin of the original nonlinear system, and I am taking autonomous case. Origin is unstable if any one or more eigenvalue of A is greater than 0. So real part, because it might possible eigenvalue of that matrix, Jacobian matrix might be the complex also. So just we have to concentrate on the real part. If that is greater than 0, then again origin x equal to 0 is unstable. So you can see here that I can able to give the condition using Lyapunov indirect method. I can talk that x dot equal to fx and x equal to 0 is stable or unstable by looking towards this Lyapunov indirect method. Anyone has confusion? Then please let me know. Silpi, are you able to follow? Okay. So Binay, Nidhi, anyone has any confusion? Have you understood the idea of theorem or not? Theorem is just telling that under which condition, okay, if I will check some kind of linear system, then I can talk about the stability of original nonlinear system. And using theorem, I can also able to tell you that under which region only this result is true. Okay, so I can talk about that. Okay, that whatever linearization technique that is only works in the very small neighborhood of the equilibrium point. Okay, and what extent that that neighborhood one can extend, that is given by that relation gx. If gx will satisfy gamma and norm of x, and at the same time if x less than r, in that particular region only I can talk about this kind of stability theory. Okay, so let us see the proof of theorem. Theorem proof is not very difficult, because now I have to check the linear system, Lyapunov function of linear system, and after that I have to talk about stability of original nonlinear system. So what I am going to assume in order to prove that theorem, first I am assuming that I have some kind of condition, and condition is that A is Hurwitz. A is Hurwitz means all eigenvalue of A, even if that is real or complex, their real part should be less than 0. And if that is there, we have already seen that if I have some system like x dot equal to ax, okay, so at that time I have constructed some kind of Lyapunov function or positive definite function x transpose px, where p is positive symmetric definite matrix. Then what happens, that it is possible to show there exists a unique p, because if A is Hurwitz, I have already proved there exists a unique p such that this Lyapunov equation is satisfied. A transpose p equal to pa plus pa equal to minus q, and q is positive symmetric definite. So we have already proved that. Okay, so and we have already assumed A is Hurwitz, so I can always able to construct Lyapunov function like this. Anyone has confusion? And could you please tell me that this is Lyapunov function now for linear system or nonlinear system? Whatever I have constructed, that is Lyapunov function for linear system or nonlinear system. Iram, could you please comment?
Sir, this is for linear system, but we can extend to non-linear only in the vicinity of the.
Yeah, but whatever theory I am going to apply, since I have constructed Lyapunov function for x dot equal to fx now, even if I will take help of linear system, but this is Lyapunov function for original nonlinear system. Okay, and after that I will see the vicinity, and I will tell that okay, under this particular, so I have region like D, and inside this region D only I have some origin, and about this origin whatever stability theory that I have concluded for linear system, that is works for nonlinear system. Okay, so basically this Lyapunov function is no longer Lyapunov function of linear system, that is for nonlinear system now. Okay, so it means that now x dot, whatever x dot I am going to use, that x dot I am going to use like this, ax plus gx, and gx, you can see that there is no approximation involved in this particular process, because I am writing x dot equal to ax plus gx exactly, because whenever I am linearizing it and if I apply mean value theorem, you can see here I haven't done any kind of approximation up to here. If approximation is here, then I can use some kind of symbol. You can see that nowhere in mathematics I have used any kind of approximation till now. Okay, anyone has confusion on this point? After that, if I neglect this, if I manipulate this, then only approximation comes into picture. Okay, so now x transpose px is the Lyapunov function for this particular system, and that particular system is x dot equal to ax plus gx. Anyone has confusion? Now what I am going to do, we know that this is energy like function or P is positive symmetric definite matrix. So two condition is obvious, x is greater than 0 and at x equal to 0 this is also 0. Now what I am going to do, I am going to see the derivative. So if you calculate the derivative, then x dot is there, and after that you can do the routine job. What you can do, you can substitute. Okay, that x dot equal to fx and fx I have represented like this. So same kind of things I have done here. Okay, so up to here I hope that you have understood the point. And after that, what I am going to do now, I am going to rearrange the term x transpose pa plus atp into x, and after that I have extra term like this. So you can see here that why I am writing this. It might possible someone might have confusion like this. X transpose p gx is here, and here g transpose x px is here, and automatically I have written this. Could you please think why I am telling that x transpose p gx and g transpose x px both are equal? Anyone? Could you please comment? Baby Dana? Baby Dana, could you please comment? Are you here?
Yes, sir.
So could you please comment why these two terms are equal? This term and this term after multiplication with this? Because you can see that one term is x transpose p into gx, another term is g transpose x into px. Why both are equal? If both are not equal, then I cannot use 2 multiply and equality sign.
So it's a symmetric matrix for that reason.
What kind of matrix is symmetric? Only p matrix is symmetric now, but x and g is not symmetric. Then why we are able to write like this? Ankit, are you here? Could you please comment why I can write this and this equal? If that is not equal, then I cannot write 2. Nidhi, could you please comment? Sunidhi, Kalol, could you please comment?
No,
Check x transpose p gx is a scalar or vector. Anyone, Iram, are you willing to comment? Okay, you can see that x transpose p gx is some kind of a scalar. Okay, why that is a scalar? Anyone can anyone can confirm why I am telling this as a scalar? Because vx is a scalar, so derivative of a scalar is again a scalar. So if I have some scalar function, could you please tell me that what is transpose of that scalar function?
Scalar, same scalar, sir.
Same scalar, so I can add it. Anyone has confusion? So either you can collect this term x transpose p gx and take the because if I assume d equal to this, then d transpose equal to d. So I can either you can see that after d transpose I am getting this. So d equal to d transpose. So I can just write 2 times. Anyone has confusion now?
Sir,
Please go ahead.
sir, sir, AX is a vector. Then how GX is a scalar also, sir?
No, I am not
If X dot
not I
AX
am
dot.
just talking about gx. I am talking about whole term x transpose p into gx. Okay, so could you please tell that this term is a scalar or vector? This whole term, multiplication of everything.
Sir, sir, it's a vector.
Okay, please check it. This is x belongs to r n cross 1. So this become 1 cross n because transpose is there. Here this is n cross n, p is n cross n. What about gx? Gx is again n cross 1. Okay,
Okay.
because how
Okay.
basically we are getting gx by fx into something x. Okay, so
Okay.
now could you please tell me that this is a scalar or not? This is r1 cross
Scalar.
1, a scalar.
Yes.
And
Yes.
means it is obvious because v dot is on left hand side. Okay, and v is a scalar, so v dot is a scalar. So I cannot equate one scalar by vector. Okay, so you can see that v dot is equated by x transpose p into gx, so obviously that is also a scalar. So if you are lazy to do that, then you can check like this. Okay, anyone has confusion? Because this kind of terminology you are going to use in whenever you are going to do Lyapunov analysis, lot of time you have to do simplification, so this kind of inequalities appear frequently. Okay, equality or inequality, here equality is there, and idea is very simple, that if I have a scalar quantity, then that scalar quantity and their transpose is exactly equal. Okay, so I hope that now you are able to understand this, and from Lyapunov equation I can now write like this. Okay, a transpose plus pa equal to minus q, and q is positive symmetric definite matrix. Okay, now what I am going to do, up to here I have equality. Now I am going to, you can see that this term I cannot give this guarantee to this term that this is positive or negative. Why? Because I know that gx, I don't know the sign of gx, I know the sign of p, I don't know the sign of x. If both has opposite sign, then that might be possible several times, so this might be positive and negative. Okay, so if that is negative, then that is okay, but positive, then that become dangerous, and due to that reason, whenever we are applying analysis, at that time we are taking the worst case situation. Okay, so in worst case what happens, that some kind of perturbation comes into picture, and whenever you are doing worst case analysis, please be sure that you are using inequality, so all terms should be has some definite sign. You can see here that I have put plus sign, and after that every term is positive, because when positive term comes here, then only v dot might become greater than 0. Otherwise, if this is negative, then that is not a problem, because first term is always negative, because 2 is positive symmetric definite matrix. So this is the worst case or worst condition. Okay, in place of gx, what I have done, I have substituted the value of gx, that is gamma, and gamma, and that is mod x and x transpose. Now I have this kind of things. Gx is basically, I have this kind of things that is bounded by norm of 2 norm, and after that here norm of this, because here abc 3 quantity you can take and norm you will take, then that is less than norm of one quantity, norm of second quantity, norm of third quantity. So basically, due to that reason, I have gamma and x 2 norm and a square actually comes into picture. Anyone has confusion on this calculation, then please let me know. Okay, I hope that you don't have any confusion. Now, if I am telling that x equal to 0 is stable, so asymptotically stable, then I have to make sure that v dot less than 0. And when one can tell that v dot less than 0, if this part, first part x transpose qx, that is negative, that is this energy function is negative definite function, or negative energy you can tell, because negative sign is here and q is positive definite. Okay, so if that is going to dominate over this whole part, then only I can tell that v dot less than 0. Okay, so under this situation, whenever this inequality will satisfy, then only I can give guarantee that v dot less than 0. Okay, and from here you can see that I have to make sure that if this kind of condition is satisfied, that if gamma, if I will select by this relation, then I can tell that v dot x less than 0, and these whole things are true in this region only, when futuristic trajectory or ball of futuristic trajectory less than r. Okay, in this way I can tell that x equal to 0 is asymptotically stable. Okay, so by the help of the bond on gx, you can see that everywhere I have used the bond of this function gx, and using that bond I can tell that under which condition v dot x is less than 0. Okay, so in using this I can able to show that if gx is less than equal to gamma norm of x and x is less than r, then only this result is true, and due to that reason v dot x less than 0 is not always true. Okay, there always exists some kind of restriction. Whenever this inequality is violated, then I cannot able to talk about the asymptotic stability of x equal to 0. Anyone has confusion on this point, then please let me know. Have you understood this derivation, everyone? Okay, if you understood this, then let us come to the second part. Second part, what we are telling that if one or more than one eigenvalue is positive, then I can tell that x equal to 0 is no longer stable. So what basically we are going to do, I have some matrix A, I am going to first calculate the eigenvalue, and I am going to cluster the eigenvalue in two parts. So whatever eigenvalue that is going to lie on open left half plane, I have actually collected that kind of matrix, and group of eigenvalue that going to lie on the open left half plane, that I am going to collect with the help of another matrix. It is possible to show that some kind of transformation, using some kind of transformation, I can collect the eigenvalue a and a2. Okay, and things it just works like this. Suppose you have something like x dot equal to ax, then what you can do, you can develop some kind of transformation, and suppose that transformation is x equal to tz, and after that I will do x dot equal to tz, and after that x dot is now I can represent x dot tz dot, and z dot is t inverse x dot. So at that moment I can write t dot, and x dot is nothing but ax, and again in place of x I am going to substitute t equal to z. Okay, so either t or so using this kind of transformation you will get t inverse at, or if you define transformation like z equal to tx, then obviously you will get this kind of transformation TAT inverse. You can see here that z dot equal to tx dot, and x dot is nothing but tax, and x I know that is ta t inverse into z. So this matrix I am telling, and using that matrix it is possible to group the those kind of eigenvalue which has a strictly negative part here and another part here. Okay, anyone has confusion? Okay, if you don't have confusion, and here negative sign I have already used, so due to that reason I am assuming that a1 and a2 both are Hurwitz matrix. Okay, so if these are Hurwitz matrix, means minus sign if I will add, then this become eigenvalue with positive sign, and this has eigenvalue with negative sign. Anyone has confusion on this point? And I have defined transformation like this. Okay, so same kind of things whatever I have written, it means that using this transformation now my system x dot equal to ax plus gx, that is actually now one can denote or group a in such a way such that I have this kind of system z1 dot equal to minus a1 z1 and plus g1 z1, and z2 dot equal to a2 z2 and g2 z2, like this. Okay, and here again I can give guarantee that gj z2 gamma and z2 that is less than r. So this kind of relation again I am going to assume that, what I am going to assume that again gj z gamma into mod z, and this z2 this part is less than r. So like this if I will write, then things become more proper, and here I have z sign is here like this. Okay, now what I am telling that here, since a1 and a2 both are Hurwitz matrix, okay, because here you can see that by adding some kind of negative sign here, in this diagonal matrix, I am assuming that A1 and A2 both are Hurwitz. Okay, this is not perfectly diagonal if I have some kind of complex eigenvalue. Okay, so both case I have considered here, and after that now A1 and A2 is Hurwitz. So again by Lyapunov equation I can tell that for every Q there exists a unique P. Okay, so I can construct some kind of Lyapunov function, and here since I have Lyapunov function, you can see that both has two different nature. So P1 is positive definite matrices associated with the A1 matrix and P2 with A2 matrix. Okay, and here negative sign is there, and due to that reason Lyapunov function now one can construct like this. Why negative sign comes into picture? Anyone can justify it? Iram, could you please justify it? Negative sign. Iram, are you here?
Yes, sir.
Could you please justify the negative sign?
Um,
Okay, you can think like this. Suppose if whole A matrix is Hurwitz, then what kind of condition? Here you can see that energy function is additive. So what I have done, I have accumulated some part using some part of energy, another part I have accumulated with different kind of energy. I can do that, and after that energy is additive, so I have added it. Okay, what I am telling, if some system is unstable, then that system is going to constitute towards the negative energy. If that is stable, then I have some kind of positive energy. Okay, so if both system is fully stable, then total energy is the addition. But if something is destructive, then some part of energy is destroyed by the system. So same kind of things I have written here. Anyone has confusion on this? And same way I can one can able to see like this. Okay, now what happens, that if z2 equal to 0 or this term is dominate over this term, it means that I have two cluster of eigenvalue. One cluster where real part is greater than 0 and another cluster where real part is less than 0. So if the energy associated with the stable eigenvalue is more than the unstable eigenvalue, then I have some kind of stability situation. Otherwise, I have instability situation. So same kind of things I have written here, that if Z2 is very small, so if Z2 is very small, then you can see that dominated energy is like this, and at that moment I have created some kind of set where this relation will satisfy Z2 less than equal to R and Vz is greater than 0. So now what I am going to do, I am going to calculate the V dot, and if you do if you means do V dot, it is possible to show same thing, because I have Z dot equal to minus A1 and after that A2 and after that Z1 Z2 like this, or after that z1 dot equal to minus a1 z1 plus g1 z1 g1 z, and after that z2 equal to a2 z2 and into g2 z. So here z is there, means that is function of z1 z2, and due to that reason you can see that if you substitute it by taking derivative, I have this kind of relation, and I know that this is nothing but pa and a transpose p, that is minus q, so minus minus that become plus, and after that similar kind of things is here, and after that 2z z transpose p1 g1 and p2 g2. Okay, now here I cannot add because both are in different coordinate. Okay, now here you can see that again, now this particular quantity is, I can tell that here this is positive definite and this is positive definite, and this quantity may have some kind of negative sign or positive sign. Okay, so these two are positive, so v dot less than 0 provided this quantity is dominate over these two quantity, because these two quantity is always positive. Okay, so what happens, that since these two quantity is always positive, so in whenever I will do worst case analysis, then I will take the negative sign here. Okay, and if you take the negative sign, it is possible to show that V dot is always greater than 0 in some vicinity of the equilibrium point. If alpha you can select like this and beta you can select like this. And what is alpha and beta? Alpha here, that is minimum of these two if you select, and after that beta is maximum of these two quantity if you will select. Then this kind of relation basically comes into picture. Okay, and due to that reason now I have V dot greater than 0 in that particular ball U. Okay, so I have V that is greater than 0, V0 is 0 and V dot is greater than 0. So now could you please tell that x equal to 0 is stable or unstable? Nidhi, could you please comment? This is condition of stability or not? What I am telling, that energy is increasing, rate of change of energy is increasing. So due to that reason, my system is unstable. Anyone has confusion on this? Then please let me know. What you can do, again please go through the proof. Proof contain lot of inequality. Just please check all inequality. If you have any confusion, then please ask me on the next class. Okay, so please drive the proof on by taking copy and paste. Okay, anyone has confusion, then please let
Sir,
me know. Please go ahead. Anyone? Okay.
sir, it was my problem. Sorry, sir.
Okay. Now let us come to the non-autonomous system. Okay, so same kind of result I am going to extend for the non-autonomous system. But please be careful. In case of autonomous system, I have talked about both result, stability and or instability. But it is possible to show in non-autonomous case, I just able to comment about the stability result, but I cannot able to comment about instability result. That is the restriction. Okay, and that is obvious because time is already involved there. Okay, so I cannot able to comment. So by linearizing, because it might possible whatever linearized system, during linearization, if time is multiplied with the nonlinear part, then that is simply rejected. Okay, and if as t tending towards infinity or somewhere, if that will dominate it, then they will destroy my conclusion. And due to that reason, we are just going to check the stability result. I am not going to comment about instability result. But in case of autonomous system, we have commented on both result, stability or instability. Anyone has confusion, then please let me know. One more important point is that if I have some kind of marginally stable system, okay, suppose if you have system like x dot equal to x mod x and x dot equal to minus x mod x, you can see that linearization of these two things are the same, x dot equal to 0. Okay, and x dot equal to 0, I can tell that equilibrium point is stable because x dot equal to 0, solution is x equal to c. But you can see that is actually I cannot able to predict that x dot 0 is coming from a stable system or an unstable system. If x belongs to R, you can see here that as x is greater than 0 and x dot is less than 0, so I am diverging. Still my linear system is x dot equal to 0, that is stable. Even if I am converging, again I have same system, and due to that reason, if something is marginally stable, then I cannot comment. Okay, after linearization, if eigenvalue is going to lie or real part of eigenvalue is 0, then I cannot comment about the stability of the original system. Okay, anyone has confusion on this point, then please let me know. So that is just proof by counter example you can tell. Okay. Now let us come to the non-autonomous system. So result is actually in straightforward. What I am going to do, I am going to consider this time, and I am assuming that f is piecewise continuous in T and locally Lipschitz in D in order to make sure that there exists a unique solution. Okay, and this function is again continuously differentiable in this particular region, whole region, and after that it means that mathematical model is only valid in this particular region. And equilibrium point, whenever we are defining for non-autonomous system, at that time we are telling that for all t, if this relation will satisfy, then x equal to 0 is the equilibrium point. Again, what I am going to do, I am going to assume that since f is locally Lipschitz and continuously differentiable, so I am assuming that this will satisfy this kind of condition. So that kind of assumption I have. Okay, so fi is continuously differentiable, so it is possible to show that f, their derivative also, so derivative of that is also continuous. Okay, so if derivative is continuous, then I can able to write like this. After that, again I will apply the mean value theorem, same like the previous one, only extra argument t is here. Okay, and t is here, and after that what happens, I can able to do same kind of analysis. Okay, same kind of analysis means since t 0, these are the equilibrium point here. Whenever we have applied the mean value theorem, you can see that this part equal to 0 by equilibrium point. So I have just this part. After that, what I have done, I have added some kind of Jacobian matrix, and I have subtracted some kind of Jacobian matrix about the equilibrium point. Okay, and after that, now here in initially ftx, because here if you calculate Jacobian matrix of this, then time is also involved, and due to that reason now this is no longer independent of time. Time dependency comes into picture. Okay, so now after linearization of the non-autonomous system, I will get some kind of LTV system, linear time varying system, as the part of this, and obviously I have this kind of term, and initially in case of autonomous system, this term is only depending on the x. Now this is going to depend on the x also, t also. Okay, and after that what I have done, same way I am going to do this. Again I will apply the inequality, same kind of inequality component wise, and this will satisfy this kind of relation. And again you can see that what I am going to do, I am going to state the theorem, x equal to 0 be the equilibrium point of this non-autonomous system, and I am assuming that that mathematical model is only valid in this particular region D, and I am just going to talk about the forward time, and the f is piecewise continuous in time, and f is continuously differentiable. Okay, so and after that what I am going to do, that Jacobian matrix dou f by dou x is bounded. Why bondedness now we are telling, because time is also involved now. Okay, so with respect to time I am telling that is not unbounded, that is bounded. And Lipschitz and uniformly Lipschitz in T, that for all T I have same Lipschitz constant D, and I have calculated AT like this. Then I can tell that origin is exponentially stable point for nonlinear system, and if it is an exponentially stable equilibrium point for the linear system. So linear system, equilibrium point of linear system is if that is exponentially stable, or if that is asymptotically stable, then original system in that vicinity, that is also correspondingly exponentially stable or asymptotically stable. So this kind of result we have. Okay, so that is just extension of the previous one, and you can see that I have excluded one part. I have excluded the instability part. Okay, and I have already told you that it might possible due to time I cannot able to generalize. Okay, so what I am going to do, in case of I am going to look towards the linearized part, and that is linear time varying system, and AT matrix whatever we have actually got, I am assuming that is continuous and bounded. So these two conditions are required in order to make sure that this Lyapunov function has a solution. Okay, so it is possible to show that this Lyapunov function, and how basically this Lyapunov function comes into picture. In previous class we have seen that for linear time varying system we have this kind of Lyapunov function x transpose p t x, and p t whenever we are talking, that is positive symmetric definite matrix, and also we are assuming that pt is bounded. Pt is obviously continuous because I am going to calculate derivative with respect to time. If this is not continuous, then I cannot able to take the derivative. Okay, so now after defining this and by taking v dot for this particular system, time varying system, we have developed the Lyapunov theory, and after that this kind of Lyapunov equation comes into picture. And it is possible to show that this Lyapunov equation has unique solution provided this matrix A is bounded and continuous. Okay, then for given q, that is qt is basically time varying positive definite matrices, and so if qt is continuous, positive definite and symmetric, then I can tell that there exists unique p, and I can construct the Lyapunov function. So due to that reason I have constructed this kind of Lyapunov function. Again, every part remains the same without the extra part, this kind of part, because pt now also comes into picture. Okay, so again you can do the same step, you can calculate the derivative, you can substitute everything, and after that what you can do, you can substitute the bond of gtx, that is x mod x2, and x is norm x, so x cube comes into picture. And after that, now you can see that if that is bounded by x is bounded by rho, then I have this kind of condition, so I can tell that now my equilibrium point is exponentially stable. Why exponentially stable? It is possible to show that if you will take this kind of Lyapunov function, so this kind of Lyapunov function is bounded by ln equality. I can already know that this is bounded by x power a and some constant here I have. You can define c1, and c1 you can decide what is your c1, because pt into, if pt is constant, then I can tell that what is exact value of c1, and c2 x2 power a, and after that what we have proved, v dot, that is again some quantity gamma and x power a is 2. You can see here that kind of relation comes into picture. Here same kind of relation basically comes into picture here, x2, and due to that reason I am telling that equilibrium point is exponentially stable. Okay, up to here anyone has confusion, then please let me know. So you have to do same kind of homework. Just now whenever we have time varying system, then extra assumption comes into picture. What kind of extra assumption? That whatever AT matrix that is continuous and bounded, that kind of assumption is required. Okay, after that whatever pt matrix you are going to consider, pt positive symmetric definite matrix, that should be also continuous and bonded, and q you will take continuous, symmetric and bond symmetric, then it is possible to show that for a the at there exists always a pt. Okay, now what I am going to show, so up to here I have developed the theory that if you are going to linearize the non-autonomous system about the equilibrium point, then how to talk about the stability of the equilibrium point of the original system, and what we have shown that original system x equal to 0 is exponentially stable, and locally, obviously locally, because this result is only true for all x that is bounded by rho. So this kind of condition we have, and you can see that based on the rho I can tell that this C3 should be greater than 2C2 L and rho, then only I can able to talk about the exponential stability. So I am able to see that under which region actually asymptotic exponential stability, obviously we can talk about asymptotic stability also, that is valid. Okay, now last part is little more interesting. Last part is telling that suppose if you have linear time varying system like this. So for linear time invariant system, we know if the real part, yeah, here I have actually keep the opposite sign, so I have to modify it. So here you can see that if less than sign is here, so I am going to substitute here the less than sign. So suppose this is less than 0, then I can tell that x equal to 0. So if I have system like x dot equal to ax, where a is not depending on time, so by seeing the eigenvalue of a, if that is strictly less than 0, real part of this is strictly less than 0, then I can tell that that is asymptotically stable, x equal to 0, or whole system, since this is linear system, that is asymptotic stable with respect to equilibrium point. Now what I am going to do, I am going to generalize it and trying to generalize it for the linear time varying system. So one might be tempted to a conjecture. We are going to form the conjecture, just I am going to extend the result of linear time invariant system to linear time varying system. Okay, and what people expect that x dot equal to at whenever I have system, so will be stable at any time, so for all t greater than equal to 0, for any, whenever I am writing, so either you can write for every, for in, for all, that doesn't matter. Eigenvalue at all have negative real part, then I can tell that, or I will expect at least x equal to 0 is the stable, okay, or asymptotically stable. But it is possible to show that that result is no longer true. You can see that I have taken very simple example. I have taken this system x1 dot x2 dot minus a e power 2t. So here this is one component is depending on t, and due to that reason this is time varying system, linear time varying system. Linear because here everywhere power is just 1. And if you check the eigenvalue and determinant a, determinant of lambda I minus a, it is possible to show that is nothing but I have two repeated value minus 1, and both are strictly negative. Okay, so what one can expect by seeing the theory of linear time invariant system, that x1 and x2 is also stable, but that is not the case. What you can do, you can just solve it. Solution is not too difficult, because why? Second equation x dot is decoupled from the first, so x1 dot equal to minus, so I have x2 dot equal to minus x2, and this is very easy to solve. If you solve it several times, I have written the solution, that is written by like this. Okay, once you know the solution, then you can club that solution here in this particular first equation. So if you club a solution on the first equation, you can see that now you have this kind of equation. And if you see this term, so this term is blowing up as t tending towards infinity. So x1 is never converge towards the 0. There exists some time t such that this trajectory will blow up. So that kind of situation comes into picture. Okay, and due to that reason, by checking the eigenvalue, I cannot able to talk about the stability of linear time varying system. And due to that reason, you have no way, you have to learn the Lyapunov theory. That is the another motivation. Okay, so up to here, if you have any confusion, then please let me know. Okay, so let us now conclude the today's lecture. What we found in today's lecture, that I have two different classes of system, means autonomous system and non-autonomous system. Non-autonomous system is a little more complicated than the autonomous system. Okay, at least in case of autonomous system, I can talk about the stability result as well as instability result. But in case of the linear time varying system, means non-autonomous system, I cannot talk about the instability result. Second important point, what we found, that in case of linear time varying system, I cannot able to talk about the stability of equilibrium point just by checking the eigenvalue. That is the another that is very important thing to understand or remember, because in several interview people are asking this kind of things. Okay, and several times those who are not those who just enter inside the research, they are doing this kind of mistake whenever they are designing some kind of means control system by taking linear time varying system. Okay, so at that time they are doing this kind of mistake. So please be aware of the mistake, and what is basic role of mathematics. If some theories fail, or you are able to generate one kind of counter example, then whole theory is collapse. Okay, and due to that reason, since we are able to talk about one counter example, due to that reason I cannot check the stability of equilibrium of linear time varying system just by looking towards the equilibrium by the eigenvalue. So what is another way out? You have to do by Lyapunov analysis. Okay, there exists some kind of result in, obviously, in literature, linear control literature, but that is not so much elegant. But by using Lyapunov theory, it is very much elegant, or same language we are using for now. You can see that autonomous system, non-autonomous system, or linear time invariant system, linear time varying system. Okay, so with this remark, now lecture is in from my side. If you have any specific questions, then please let me know.